fine. What's up, dude? Hello. Starting off with number 2 here. That's the diagram for it. We got like a torque applied to a rod, which is then connected to another rod via 2 gears. And we are looking for the diameter of shaft AB, which is the bottom one, which the torque is being applied to. So we can do these with these equations that we were learning about the past week, where shear stress is equal to the torque times the radius over J, which is like the moment of inertia. We can expand out the moment of inertia J to pi over 2 times r to the 4th, and then from there we just isolate for r and plug in all of our givens, and we'll get that the radius is equal to 0.022 millimeters, and then to find the diameter we just do a little conversion and we get that it's equal to 44 millimeters. Then for part B we're trying to find, let me do some clarifying. For the first part we're trying to find along this bar that it's being directly applied to, this being this like red thing being the torque. Now we're trying to find on this bar, the upper bar, which is connected by those gears. And we'll do that by making a slight difference to the equation, this K, which is like a ratio between the radiuses of the gears. And so literally we just take these 2 radiuses, 240 over 80, and that's literally the whole thing.
So how did you know like which one to put on top and which to put on like the bottom?
I just went over because like we're looking for, I don't know how correct this is, but sorry. I should have just drawn the diagram.
Wait, blow it. Can you make it bigger?
Yeah, probably. Yeah. Oh. So my intuition was like we're solving for this bar.
Yeah.
So we should put this one on top. It was like a ratio.
Well, I also think logically, like, the way I thought about it, I was just wondering how you thought about it. The way I thought about it was like if we look at, like if you're applying the torque to this smaller gear and then it's applying to the bigger gear, obviously the torque is going to be amplified, like just logically, you know what I mean?
Yeah, that makes
Like
sense.
mechanical advantage?
Yeah.
Is that the right term?
I don't actually know.
Is that how? I don't, yeah, if that's how gears work.
That makes sense. I don't know.
Yeah. So mine was just thinking logically, and then you're gonna apply the ratio. But yeah, that makes sense.
Yeah, and then you like there's like very small difference between the 2. That's all.
Gotcha.
Very cool, very cool.
All right, moving on to number 1. So number 1, we have a little box. I don't know what material this is made out of, but they gave us the
Red cedar
property
wood.
of it. What?
I think it's actually cold rolled yellow brass.
Thank you. What's this E stand for again? What does that mean?
Is that Young's modulus?
Thank you. Yeah. So they gave us the Young's modulus of the property of the material, and what we're asked to do is there's this force P applied on both sides. That's going to be 40,000 pounds, I think it was, and they're applying this force, and so they're asking how this slope that's like drawn onto the material is going to change after there's a given force applied. So right now the slope is obviously 0.4, but we're wondering how it's going to change when we apply that force. So the first thing we're going to find is the change of the length of it, and that's just a simple Pli equation. So we just have our length, Young's modulus, and then the area. It was a 1/4 inch thick, so 6 over 4. And then we're going to get a displacement value. So that's how much the length has changed. And then we can go ahead and use, what's this called, Poisson's ratio, to find out. They gave us the Poisson ratio. They give us that it's equal to 0.34, so then we can go ahead and find out the other component to find out how much the height is changing, and we're going to get that number right there. I believe these are in inches, by the way. I forgot to write the units, my mistake. So then once we have the 2 displacements, we can go ahead and set them up as a ratio to find out what the percent change to transfer it to this triangle right here. So we have the percent change of the height and the percent change of the length, and then we can go ahead and reconstruct those to find that it was 1.002, so it's a like 0.2% change, and then a 0.06%, so very, very small changes, but it is applicable. And then putting it into our formula for the height, this should be 10. Let me get a marker. Putting that in for our triangle right here to find the new slope, we get 0.4007.
Okay.
But yeah.
Now I got a question. I feel really dumb about this, but I got the right answer because it's asking for a slope. So I was like, oh, you just do rise over run. So I did 4 over 10, and I got 0.4, which was correct.
Okay, so
That worked for every problem.
No. I like the way you're thinking, kind of. But you, but you have to keep in mind, obviously, this is going to change when we apply a force to it. So it's going to be under a stress, so that means there's going to be a strain applied to it. So you can see the length is changing, so obviously the slope's going to change, and depending
it's
on
built off those two values, so it's like that plus the chain. Okay, I see. It's just it was such a small. Is it 'cause it was such a
Macmillan,
small
like,
value?
rounded
Yeah.
it
So yeah, the reason though, and the way that the program works is they have, I think it's like a 2% error threshold. So obviously, since this value is so small, so close to the original 0.4, that threshold is going to be met by putting in the original. But you can
there's
see
like a
there
huge
is
change on it.
there is a slope change. Yeah. So you can see like proportionally, the height grew more than the length. And that comes down to this ratio right here. So that's just a property of different materials.
Can you imagine getting something wrong on a test though, and your answer was off by 0.0007, and you got like no credit?
Well, yeah, you'd get no credit even if your answer was right because you had no work. You're just like, yeah, rise over run.
I just thought up the answer.
Yeah.
All right.
Well, good job then.
Good work.
Want to switch it?
Yeah, let's flip her around. You have like a jammed wheel, bro.
All right. I'm Case. I'll be doing number. Oh, this should be 7. Number 7. So we have a gear, 2 gears, just like what was this, number 4, and they're kind of rotating each other. But it gives us that the max torsion is 60 times 10 to the 6 megapascals, and we have a maximum angle too somewhere. Oh, here, which we convert to radians. So it's asking us what the maximum or the required diameter of the shafts are to rotate. So let's see. So we have 2 equations that can solve for this diameter. We have one using the angle it gives us, and one using the maximum torsion it gives us. So we have both equations, and we're given every value for those equations too. So using both equations, for the torsion one, we get a value if you plug in all your values. And for the angle one, we actually do angle of AB for one length and CD for the other length, and you add both of the angles to get your final angle. And and so you get another diameter value for this like type of approach, and you're gonna use the higher value here out of the 2, because if you use the lower value, it just won't turn because it's not.
Because it's asking for the minimum required. So in order to meet all of the requirements, you have to use the higher. Okay.
Yeah.
And then so for your angle change, I guess I think what I was missing is that it's dependent on both of the shafts, like the torsion.
I guess I didn't explain that well. So for the angle, they're both going to turn at the same angle when they rotate. So you can just use the angle that you're given and say that the angle that both of them turn equals the TC over JG for both gears.
Okay. Where's your C in this?
So C is in J. Sorry, I forgot. J is
I see.
pi over 2 C to the 4th. So you just plug that into every J.
Okay, that actually makes a lot of sense.
But here, you're supposed to use. So I forgot to explain this too. We're given a T value, but we have to calculate it for AB. So there's a ratio.
We use that tension on both of them?
Yeah. Because if it's on one and they're both attached, it's going to be used on both.
Wait,
So
that makes so much sense.
You have to calculate it, and you end up getting a higher value. If you got a lower value,
So that goes back to the one, I think it was Evan's problem, where the gear ratio is amplifying the torsion. But here it's applied to even the original shaft because it's all one system.
Yeah, even though this is applied,
That actually
the other
makes a lot
one
of sense. Wait,
just
yeah.
amplifies this one. So it ends up both use this torsion. That's why you use both
Amazing.
values.
Wait, that makes so much sense, yeah. Thank you.
Yeah, I definitely messed that up my first time.
Yeah, I tried CD here, but you gotta change it.
Okay. Thank you.
Yeah.
Oh, I'm still on this side.
Yeah. Oh, my bad.
No, you're good. This was number 4 through 5. So for this one, it was similar to a question we actually had in class. So there's like a motor over here, and then there's a rod that goes through these 2 discs, and then they're attached to like a rotating. It's like a fixed point with like I assume like a rotating collar, and basically we're looking for the angle of twist between. In this case, it's going to be B and D for this first problem. So this rod in between. We're going to use our angle of twist equation. Phi is equal to TL over JG. In this case, J is our polar moment of inertia. And one important thing to remember is when you see these equations and they use C, we messed this up when or at least I did when I was going through this, where C always means radius in this case. D is diameter. So
Do you know why they use C instead of just saying R?
Well, actually, yes. C is the maximum radius from here, and if you don't use C, because you can calculate the angle using like any radius inside the circle, which is rho, but C is just the maximum radius, which is like
Oh, so
what we're
C just means
calculating.
R max.
Yeah.
Okay, thank you.
there you go. So remember that, because otherwise this equation would look very different if it was diameter, which is why we have C is equal to 1/2 D. Yeah, it's a simple radius equation. Now we're going to plug in everything in. So our T in this case, we're looking for the angle of rotation, the angle of twist between this rod, between these discs, and each of these discs have a different applied torque. So we're going to add those for our T. Our L is going to be the length of the rod. Make sure you convert millimeters to standard meters. We're going to plug in our J, our radius, and then our G was given. And you'll get a radian value. Make sure you convert that to degrees if that's what they ask it in terms of. And for the next one, I don't have it written here, but for 5, we're doing, similarly, we're doing the angle of twist, but it's going to be on the rod. So there'd be like a motor here, and then the rod would continue, and it's on this rod. And
So you're just adding them together.
yeah, so this can also be the sum. So when we're looking for the angle of rotation, sometimes, as Case actually did here, we would sum up the multiple angles of rotation. So for this one, I got like 3 point something. So that's bigger than 1.21 because we're adding.
And you would add them, not subtract them?
Yes. Yes.
Sorry, are you done?
Yeah.
I think the motor in this problem also had its own
Okay, yeah.
torque. I think it was like 500 or something that you also account for. Did you have a-
I was just looking back at this one, and is this negative on purpose, or is that a smudge?
No, I erased that. That's just positive.
Okay. That's just, okay,
I
yeah.
accidentally erased it, yeah.
Okay,
That's,
okay.
that's just a line.
Okay, yeah. Anybody else have any other questions?
I think that's good.
All right, beautiful.